Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our distinguished speaker today, Professor Sham Kakade from University of Washington. Professor Kakade is a Washington Research Foundation Data Science Chair with a joint appointment in the Department of Computer Science and the Department of Statistics at the University of Washington. And he is also a co-director for the Algorithmic Foundations of Data Science Institute. He has made tremendous contributions in mathematical foundations of machine learning, reinforcement learning, and AI in general. For example, his contributions include laying the foundations of the PAC-MDP framework for reinforcement learning, and one of the first provably efficient policy search methods called conservative policy iteration, developing the mathematical foundations for linear bandits and Gaussian process bandits, tensor and spectral methods for latent variable models, and the design and analysis of numerous convex and non-convex optimization methods. Moreover, he is a recipient of the IBM Goldberg Best Paper Award in 2007 and the INFORMS Revenue Management and Pricing Section Prize in 2014. He has been program chair for CODE in 2011. Today, he's going to talk about representation, modeling, and optimization in reinforcement learning. Please join me in welcoming him.
All right. Hi, everyone. You can hear me, right? Okay, great. Yeah, thank you very much for having me here. And a big thanks to the organizers for putting together this really vibrant seminar series and keeping it up online, which is especially important right now. So it's a real pleasure to be here and be a part of the series. So I'm going to be talking about a number of questions in reinforcement learning. So reinforcement learning, it's the study of how an agent interacts with a possibly unknown environment to gain long-term reward. Okay, and it's become one of the dominant paradigms for artificial intelligence. And it's really relevant to a host of both technological applications and applications for society, because the things we care about now are not just static algorithms, but they interact with the world. They're going to gain information, and we would like them to be robust and to automate this procedure for more effective reinforcement learning. Okay, so let's start by jumping in and looking at the formalism for reinforcement learning. Okay, so this formalism is the Markov decision process. So the Markov decision process is defined as follows. Okay, so we think of an agent, so that can be like this, us, the person, and we're going to take some action. That action is going to impact the environment, and we're going to take an action in some state of the world, and then after we take the action, the state of the world is going to transition to some new state in the world under some stochastic transition matrix. We're going to observe some reward, and the system's going to repeat for some number of steps. Okay, so that's a Markov decision process. Why is it Markov? Because the next state we get to is stochastic, and it's only a function of the current state we're in. Okay, and just some definitions. So a policy or a behavioral policy, that's a mapping from the state we're in to the action we take. We're going to execute a policy pi to obtain a trajectory. A trajectory is just a sequence of states and actions of reward that we observe along the way. So, we started as 0, we take a 0, we see the reward, we transition, so on and so forth. And our objective is to maximize some notion of long-term future reward. For example, the discounted reward, where this discount factor gamma is less than 1. Okay, so we're interested in maximizing a long-term future reward. And in terms of definitions, we're going to say V pi at S0 is the value that we obtain it's the value we obtain starting from S0 and executing pi for the horizon. Okay, and what we'd like to do is find some policy that maximizes our long-term future value. Okay, so that's the basic setting. Okay, so our goal is, find some policy that maximizes the long-term future value. Okay, and there's a lot of challenges here. So let's go through some of these challenges. So, we could be this robot wandering around. Well, the environment might not be known to us. So we're going to have to do some kind of exploration. There's this problem called the credit assignment problem due to delayed reward. So, for example, if we get this reward -1, we have to figure out what caused the problem. Was it because we went down here? Was it because, an action over here that we took? And we don't get immediate feedback like we do in supervised learning. And of course, adding to these challenges, we have the problem that our state space is very, very large. So this is a pretty impressive demo from OpenAI less than a year ago, where they got pretty good at manipulating this Rubik's Cube. And it's not the algebraic solver that matters here. It's that dexterous hand manipulation is a very challenging task. So I can play the video here. Maybe I need to change. Okay, there we go. So this is a dexterous hand manipulation task. The state of the system is the various joints, the velocities, the configuration of the cube, and the actions are like the forces we're going to put at the actuators at every joint. Okay, and this is clearly both a high-dimensional state space, maybe not super high, like 100 dimensions, but it's an infinite set of states because these states are continuous. Okay, so it goes on to solve it, and for me, this is impressive because even though they're using a simulator to train this thing, they're actually transferring to the real world, and dexterous hand manipulation is one of the most challenging robotic tasks out there. And we're seeing real progress in reinforcement learning utilizing these methods. So we really want to push the frontiers of what we can do, make this more stable and widely accessible. Okay, so let's just take a step back and understand some of the challenges we face in doing this. Okay, and to do that, it's going to help. It's going to help to get a perspective of thinking about reinforcement learning and its relation to supervised learning. Because maybe about 8 years ago or so, almost a decade now, we really got to kind of deep learning phase 3. There was sort of waves when deep learning was popular, and it was popular. But somehow in phase 3, what happened was we got extremely good results on supervised learning, and this really created just a revolution in what types of problems we were capable of making progress on. That eventually extended to deep learning, that eventually extended to reinforcement learning. But there's a couple of challenges here. Okay, so let's think about this perspective of going from supervised learning to RL, and then we'll dig into the details of the overview of the talk. And the talk's really going to be highlighting some of the challenges we face in RL along with solutions. Okay, so a couple more definitions will help us. So I already defined this value function v pi of S0. That's again the value that we get in expectation by executing policy pi from S0. There's another concept that's pretty helpful, which is the state action value. Think of this as just like a one-step look-ahead value. So I'm at state S0, then I take action A0. Okay, so I don't follow pi. I'm going to possibly deviate from pi and take A0. Then I'm going to get my expected future reward by following pi. So think of the state action value as like a look-ahead value where I'm going to deviate from pi by taking action A0, and then I'm going to follow pi. Okay, so that's a helpful definition. Some other things, we're also going to refer to S as the number of states in the world. S could, in fact, be uncountably infinite or very large. A is going to be the number of actions, which also could be large or infinite. And you can think of like the effective planning horizon as 1 over 1 minus gamma, because we're discounting it. And as this discount factor goes to 1, we're going to be accumulating rewards over effectively a time scale of 1 over 1 minus gamma. Okay, so this is just a couple of things to keep in mind. I'll refer back to them as well. And sometimes I'll refer to the state action value as like a one-step look-ahead value, because that's a little more intuitive. Okay, so let's actually look at how we solve a Markov decision process if we know the model and the states and actions were small. Okay, this is the classic tabular dynamic programming concept. Okay, so what do we do here? What we do is we're going to make a big table. So hypothetically, let's think about how we solve this Rubik's Cube problem with dynamic programming. So this really is like this classic solution concept. So what we do is we make this gigantic table. The first column is the possible states we're in. So what are the states? They're going to be like the joint angles of the hand, the cube configuration. So we write down every possible state of the world. And then we write down every possible action we could take in the second column. So these are like the forces that we place on the actuators in newtons. Okay, and then we start with some policy. So this algorithm is going to be iterative. So we start with some policy, and then in this third column, for every state in the first column and every action in the second column, we're going to compute this the state action value, this one-step look-ahead value, right? So we're going to compute, how well we do at S, taking A, and then following pi. Okay, so that's the first step in the algorithm. So step one. Okay, we compute this Q pi. Okay, then we go to a policy improvement step by updating pi in some greedy way with respect to Q pi. So this improves our policy. Then we go back to 1 and repeat. Okay, so this is the classic policy iteration algorithm. And what's the problem with this algorithm? Well, why is it good? It's good because if we had a model of the world, this will actually converge quite quickly to the optimal policy. Okay, and the reason it's implausible in practice is because, well, we might not know the world. And the even bigger problem is, of course, that this table, for this case, is uncountably and infinitely large. Okay, so what is the approach we might take? Well, one idea that's popular is let's use these neural networks to handle this large infinite table, because as we know, these neural networks are very good at the problem of generalization. So let's try to utilize them for dealing with this very large table. Okay, and this is not a new idea. It goes, in terms of theory, this was the motivation for this classic book by Butsekas and Siklis, which really was one of the first systematic perturbation analyses of RL with supervised learning. But their motivation really was what would happen if we had these universal function approximators. And the idea of using connectionist-based methods for AI and RL actually goes back further. So it's kind of a very old idea, but it's come back in full force because of its success. Okay, and how do we use these methods in reinforcement learning? Well, one of the most popular approaches, both in supervised learning and in reinforcement learning, is actually policy gradient methods. Okay, so what's a policy gradient method? It's you start with some policy, you compute your gradient, because what do we want to do? We want to optimize a value function over some space of parametric policies. So the standard thing to do is, try to compute a gradient and do hill climbing. So it's a local search. And in practice, this works very, very well in many problems. Okay, and just for perspective, a couple of policies that are very natural for us to think through are these kind of policies of the form that you the probability of state A, probability of action A in state S, we're going to write it as exponential of some function. Okay, and some natural functions to think about are like the Softmax policy class. So this is a policy class that for every state and action in the world, we have a parameter. Okay, so this is a policy class that can represent every possible policy in the world. And obviously that's too rich of a class. A very nice class that's a little more richer is this log linear policy class, which is the usual thing we do. We come out with some features and then think about linear representations in these features. Okay, and then our log linear policy class is going to be proportional to that score. Okay, or this function could be a neural network. Okay, so this is one class of methods we use reinforcement learning. Okay, and kind of before going on to the overview, let's just step back and say, how should we think about these methods? And what are some of the differences, again, between how we do gradient-based optimization in supervised learning and those in reinforcement learning? Okay, so just a couple of differences more generally between supervised learning and reinforcement learning is that in supervised learning, like, look, our distribution's fixed. We have a set of inputs given to us, and for each input, we have a label associated with it. Like for every image, we know what if it's got a terrier or whatever type of dog is in it. Okay, and in reinforcement learning, there's no fixed distribution of our states. The states we get to are really determined by our policy, and no one tells us the correct action at every state. Okay, and really due to this, computing gradients is non-trivial because you just don't have this offline data set to compute a gradient. You have to actually do some kind of Monte Carlo or simulation-based method to get these gradients. Okay, so these are essentially generic differences between supervised learning and reinforcement learning. But let's jump to some more technical differences between RL and supervised learning with regards to the optimization landscape. Okay, so in supervised learning, gradient methods, in particular stochastic gradient methods, they rule. They're the predominant method. Everyone uses them. It's extremely effective. You just concoct your big neural network, run gradient descent forever. It's non-convex, but any practitioner, like, look, we aren't bothered at all by non-convexity in the space of supervised learning. And these vanishing gradients, they don't seem to be a problem with various initialization tricks. We have theory now for saddle points, but to a large extent, no practitioner is going to balk at having a non-convex optimization problem. But somehow in the reinforcement learning land, the picture is very, very different. So the claim now is in reinforcement learning, this saddle point picture is really false. And somehow this isn't some theoretical thing. Practitioners know this in the back of their minds somehow. So somehow when they're doing supervised learning, practitioners aren't at all bothered by non-convexity. But in RL, why they don't explicitly say they're bothered by non-convexity. Everything they do in practice clearly reflects this. And this is because in reinforcement learning, this vanishing gradient problem is very real. So in particular, in reinforcement learning, the problems we care about could actually have very flat gradients. And these gradients can be flat not just in terms of this picture here of this like nice data point where you perturb things and you're fine. Your gradients in reinforcement learning can be flat like all the way down. For very, very high orders, you can get flat gradients. Okay, and you can come up with examples like this. So for example, here's one such case where if you try to run a gradient method starting from S0 and you initialize the agent randomly, you're going to be stuck. Why? Because two actions take you to the left, one action takes you to the right. The reward is at this rightmost state, and there's no reward in between. So if you start randomly, your gradient is basically zero because any perturbation you make has no impact on the reward. Okay, it's even worse because it's not just your gradient is zero, your Hessian is zero, the third derivative is near to zero. It's like all the way down to very, very high orders. This optimization landscape is very, very flat. And this is true in like very hard problems too. Take some robotic system and you want to get a humanoid to stand up and the reward is at the top. If you perturb it randomly, it's just going to stay on the ground, possibly with no reward. Okay, and you aren't going to solve this by just twiddling the parameters randomly. Okay, so the optimization landscape in reinforcement learning truly is different from the challenges we face in supervised learning, and this is because of this problem of exploration. Okay, so the challenges are different for a variety of reasons, and and on top of all of that, remember we want to deal with these issues with regards to this curse of dimensionality, that we have to deal with this large infinite table, and we have to deal with the fact that we have these optimization issues, we might not have a model of the world, and so on. Okay, so the talk is really going to highlight a couple of ideas for how we think about issues in reinforcement learning. So we're going to briefly touch upon 1 and 2, which is the first question is how do we think about representation and what good representations mean in reinforcement learning? Because in classical supervised learning, there's a lot of ideas about VC theory and notions of complexity, whereas in RL, these notions of complexity are far more subtle. Then I'll take a brief break looking at the smaller tabular case and just ask an information theoretic question, which is how many samples do we need to observe to do reinforcement learning? Then the bulk of the talk will move into understanding optimization, in particular, like why are gradient-based methods so successful given what I showed you before? Because that problem, you're stuck. And this is not a high-dimensional problem. It's a small state space problem where a gradient method could be stuck. Okay, so, and for the organizers, yeah, feel free to jump in if you have like clarification questions. So let's just jump in and look at the question of representation and what we mean by this. Okay, and I'll start with really just an example of what a representation might be, trying it out on on some benchmark robotics problems, and then just ask a little more abstract theoretical question of what we might want with regards to having a good representation. Okay, so a few years ago, we had these benchmark tasks of moving these various things around. So this ant, you want this thing to wander around maybe quickly. You want this hopper to jump up high. And these were in this Majorco simulator. It was a physics-based simulator. And this is one of the precursor to a lot of these successes we're seeing now with deep RL in robotics. So the goal was to try to find policies which worked very well on these tasks. Okay, and rather than jumping to neural policies, let's just look at what happens with some linear policies on a reasonable feature space. Okay, and see what we mean by representation. Okay, so what we're going to do now is rather than applying deep learning to these tasks, we're going to just run a naive policy gradient method, and we're going to do it on this log linear policy. So this is one of these candidate policies I mentioned earlier. So this is going to be a policy where we have some features. So this is going to be like, the states of the system, like the center of mass, the joint angles, and so on. We're going to put those features in a vector, and then we're going to say the probability of like taking some force at some angle is proportional to e to some weight vector theta dot these features. Okay, and then we're going to try to do some kind of hill climbing approach to optimize theta to get a good policy. Okay, and this is a very low dimensional policy because phi is only about 30 dimensions. Okay, so and this definitely is avoiding this gigantic Monte Carlo approach, and it is definitely much simpler than parameterizing things by some gigantic neural network. Okay, and what happened on this setting? So we can, I can ask you to guess the policy. So one of these were trained with linear policies, and one of these things were trained with a neural policy. It turned out for all of these benchmark tasks, these raw features actually got to state of the art. So it's a little surprising historically that these features were good enough, but there is this feeling that in many cases, if your features are okay, you'll often do well. And what this shows, it's more than just the features are okay, the policy gradient methods as well were fine to get a good policy. Okay, so yeah, this might be an easy case, but on the other hand, there are cases where you can just have some features that are lower dimensional that work well. Okay, and the question would be more abstractly is what types of features might we want that give us a good representation? Okay, and in supervised learning, we don't really think of, we often just take some representation and we don't make strong assumptions about the world. Okay, but what we want here is to understand what are the properties of the features such that, maybe our features can be low dimensional and help us deal with this curse of dimensionality. Because we could have an infinite set of states, but our features could be low dimensional. And what we would like these features to do is help us to generalize and actually solve this problem with the number of samples or computation time that is not, say, exponential on the horizon or polynomial in the number of states and actions. Okay, so when I mean by horizon here, I actually mean 1 over 1 minus gamma. So that's the effective horizon. Okay, so now I'm going to look at a slightly different assumption. So now we're going to look at the theory of what it means to have a good representation. And while I used these features before to talk about policy learning, now let's think about the features as approximating value functions. Okay, so these are going to be these one-step look-ahead values. Now, I'll come back to this connection later between values and policies. But one very nice property of your features might be that they can well approximate your state action values. So these are these one-step look-ahead values. Okay, and let's suppose for a moment, for every policy, these features could well approximate the state action values everywhere. Okay, so there's a sense in which what I wrote here is a very strong assumption, because this says this is a max over SA, so it's like an L infinity norm, but it says for every SA we have there exists a weight vector which that approximates this state action value. Okay, and in words, what's that saying is if we think about that iterative algorithm with that big table I showed you before, and we wrote that function Q as one of those columns, this is saying that last column Q lives in the span of a small set of features. Okay, and with some error epsilon. Okay, and this is a much stronger assumption than we make in supervised learning. Okay, and what I'm going to argue is even with this strong assumption, if our dimension is just, plausibly big, like 1 over epsilon squared, which isn't all that big, you might not be able to do reinforcement learning. And we proved this formally, that there's kind of a hard threshold on how good these features need to be to do reinforcement learning. And what this result says is that suppose this strong condition above was actually true. Okay, even with this condition, you might need a number of samples that's exponential in this horizon h. Let me just go ahead and fix this now to be. Clear what I mean by this? Okay, so under this assumption, which looks like an extremely nice thing to have. Like in supervised learning, we would never dream of assuming that the true target function is like perfectly linear everywhere. But in reinforcement learning, if there's just a slight bit of error, where that error is past some function of the dimension, but this is again the dimension of the features, you can't do reinforcement learning, meaning that the number of samples you need is going to be exponential in this horizon. Okay, so then you're back to basically just doing the tabular algorithm. Okay, so this is at least giving us motivation for why when we study reinforcement learning, we might need to start thinking about the structure in the world which allows us to solve the problem of generalization. See, somehow in supervised learning, these notions of VC classes and things like that tell us when we can generalize. But the notions for when we can generalize in reinforcement learning are going to be much more subtle and stronger. And lower bounds like this are very informative. And I think the important thing I want to emphasize here is that this lower bound, it is not pathological. And I think it's actually very relevant in practice, because what's going on is that at this threshold we have, you can almost make a random construction showing almost all of your features are actually pretty darn good in approximating this problem. Yet the way your errors propagate, you can show is gonna destroy any algorithm. Okay, so so this problem is not really a problem of exploration, because we can actually know the dynamics in this construction, and it's not a problem that our representation isn't good, in that our representation is pretty darn good. It's just that this dimension of our representation is just a hard threshold, that we actually need this dimension to be kind of smaller than some function of epsilon before we can do anything non-trivial. Okay, so again, for the organizers, feel free to ask a question, if a clarifying question if you have one. But I think that, for me, I think this result is revealing, because if you look at the history of RL, we're trying to make various assumptions that can say, hey, we can avoid this curse of dimensionality, but we don't really have a good sense of why we need to make these assumptions. And lower bounds like this are telling us why we need to impose certain assumptions. Okay, so if you watch the slide offline, you can look at the slide, but there's further readings, and there's a lot of work with regards to upper bounds of trying to say what types of structure permit generalization. And this is trying to couple those two so we can see why we need certain assumptions. And this does change the way we think about this problem of dealing with this infinite table, because it's far more subtle in the case of reinforcement learning. Okay, so this is some of the basic points with regards to representation. It's definitely subtle, our notion of complexity, and there's really hard limits as to how good the features we need for reinforcement learning to be possible. Okay, so
so before you jump to the next part, so maybe I'll interrupt you a bit by asking two questions. Great. So the first one is that for the linear policy, are the features fixed? That is phi fixed? I think the answer is yes, right?
Yes.
So does it solve high-dimensional problems? That's the question.
Yes. So the hope, in a sense, for representational learning, if we think about, so let me do this by an analog of supervised learning. Okay. So in supervised learning, the hope is that if we had a good representation, like on these ImageNet kinds of things, you can take the top layer of your classifier, and then when you apply them to new problems, you can learn very cheaply. Okay, so the way you do transfer learning and supervised learning is it's actually learning on a low-dimensional problem. Okay, and one might hope in reinforcement learning, something similar could happen, that if you could somehow learn a good low-dimensional representation, then you might be able to do well on new problems. Okay, so this is an empirical question. But it is the case that the neural nets people use on more challenging questions, the top layer of this network is actually is not particularly wide. It's actually pretty low width, and that does suggest that there might exist pretty good representations. And I think this is a good question for further work. This sort of coupling of learning the features and the reinforcement learning. But yeah, it's a great question.
Okay, and another question is, could you please give any intuition on why we incur an exponential dependency on the horizon, even if we know the dynamics?
Yes, so the reason we know the dynamics here, but we don't know the reward. Okay, so the construction is really a tree. We know there's a reward somewhere in this tree, and the problem is the way this construction works is it just isn't revealing, even though it can fit every policy on this tree perfectly, somehow the way the construction works is you still somehow can't query the nodes along with your feature representation to reveal where the reward is, and this is really somehow due to like a Johnson-Lindenstrass proof that the way the JL is going to work is somehow you can uniformly approximate the value of every policy. And still you weren't going to be able to find where that reward is without kind of querying every node. Okay, so the hardness is really coming from this, it's kind of some kind of core set that they call in like computer science, the rigidity of matrices, but it's kind of hidden in this reward, and then you just get stuck. So, I definitely encourage you to look at the paper, because the construction is actually very, very simple. It's literally just take a deterministic tree, take a random projection of all the nodes to approximate the value function, and random projections are pretty good at doing that. And there's a reward at one node, and you're just stuck. So.
Okay, that's all the questions.
Great, thank you. Okay, so now I'll take a quick break and just look at the question of sample efficiency in the tabular case. So before we jump to policy optimization, a basic question is going to be, how many samples do we need to observe in order to do reinforcement learning? So now let's consider a case where we might not know the dynamics in the world. And let's actually suppose we're in this tabular case where the number of states and actions are small. Okay, and we could ask, what's the minimal number of samples we need to observe to do reinforcement learning? Okay, and we could also ask, does a model-based approach work? And given time constraints, I'm not going to go too much into this particular slide, just pointing out that there are many settings that if you have a model of the world, you can do planning in this model. So this is just a simulator that if you have a simulator, you can actually try to do planning with various look-ahead approaches. And if you're smart about it, it can work extremely well in various control tasks. So this is one of these precursor methods for this Rubik's Cube solver of showing how we could exploit a simulator. So there is some settings where there's a lot of value in trying to build a model, but even ignoring that question, there's this really old information theoretic question, which is, suppose you could sample states and actions in a next state wherever you want. Okay, so you can construct an estimate of these transitions by somehow just asking for a sample in various state action pairs. This is called this generative model. Okay, a very basic information theoretic question, which is just how many samples do you need to observe, or like how many transitions do you need to observe before you can discover a good policy. So I don't want to observe transitions necessarily to build a model of the world. This is just what is the information theoretic limit of what I need to do, what I need to observe in order to find an optimal policy. Okay, and this is really one of the most basic questions. And on top of that, you could ask, when I get these transitions, is the right thing for me to do build an empirical model? Okay, and this has been an open question for quite some time. There was a line of works, many not even cited here, kind of leading up to both what is the optimal rate, and on top of that, can just a naive model-based approach do it? For example, observe my transitions, estimate an empirical model, and plan in that model. Okay, and it turns out this has been recently resolved, and it shows that in fact, a model-based approach, at least in this tabular case, is minimax sample optimal. And the number of samples you need is just linear in the number of states, the number of actions, and cubic in the horizon. So it's cubic in 1 over 1 minus gamma. Again, what's interesting about this is it says you actually don't need a particularly good model of the world to do planning. Your model can actually be very, very sparse. Okay, because with SA samples, you really don't have a good model of the world. Again, more recently, there's a subsequent paper to this one, just sort of sharpening the epsilon dependence. So there's a real sense in which this optimal number of transitions has pinned down quite sharply. And it's worthwhile looking at some of these papers, because you start realizing that even in this basic analysis, there's some pretty delicate probability theory questions to get right. And then we can go to harder questions of, like, suppose we don't have this generative model, what's the optimal rate? And offline I'd be happy to discuss more, but there's a number of very difficult, just straight up questions for probabilists for how we do these analyses, that if we had those tools, I think they would help us with many questions downstream with regards to like data reuse and so on. Okay, but I'll just leave it at there, that as like a little break, that even basic questions in low dimensions are very tricky, and even this one of just the optimal information theoretic rate has been resolved only very recently. Okay, so let's just jump on to the last part of the talk, and just taking time. Yeah, I have a good enough time to get through this. So we'll look at this question of optimization, because this is kind of where the rubber meets the road. Like the tabular part, this is a question for probabilists. This representational question, this is fundamental, but this kind of isn't where the rubber meets the road. Where the rubber meets the road is, I want to get something to work. What do people do? They use policy gradient methods with various tricks. So why is this working, and can we improve it? Okay, and let's take a look. Okay, so before we jump into some theory, let's look at some videos again and see why issues we face in policy gradient methods are quite related to robustness. Okay, so what I'm going to do now is take one of these demos from before, this Hopper demo, and I'm going to like kick the system and see if it recovers. Okay, so we perturb it, falls over, and this is a policy we've learned, it doesn't seem to get back up. Okay, we have this walker is running, we pull it, it falls over, it can't get back up. Okay, and this is true regardless if we use these linear policies or neural network policies. You train them to do well from one particular start state, but then you kick them over, they fall to a different configuration, and they can't get back up. Okay, and this is really an issue of robustness, because if you're trying to get this hand to manipulate something, there could be other outside forces, or the simulator might not be correct to push it somewhere, and then you're going to be doomed. And this actually happens in practice. Okay, so how do we fix this? Well, one idea is, rather than just training from this given start state as 0, you train to optimize this model from a diverse set of configurations. So rather than starting at one configuration, try to start it in all the places it could get to under perturbation, so under this mu. Okay, and in this particular case, it fixes this problem, that if you don't train it just from S0, but train it under various different configurations, it does quite well. And in the RL in our RL toolkit for these control problems, this technique is basically called domain randomization. So in this OpenAI task, they actually trained under various different models and under various perturbations, because you want the simulator to transfer the real life, and you want it to be robust to various types of perturbations. So it's not perfect, but there's at least some pushes that make this thing robust. Okay, and what they did was they really trained over a diverse set of models and configurations, and they just ran gradient methods rather than from just the starting configuration, but they tried to optimize under lots of different configurations. Okay, and while this is for robustness, I'll argue that this is actually very relevant for optimization as well. So let's go back to this hard instance. The problem is that our gradient is 0, but suppose we could cheat a little, because suppose we had a simulator or someone was going to help us, and rather than initializing this little person at S0, we had a start state distribution that spread where this person started throughout, say, these S states. Okay, so some of the time the agent would start here, then just randomly taking actions that'll get rewarded. Okay, and if you think about this, you might hope that if you started everywhere, then some of the time it'll start near the goal state. Those times when you act randomly, it'll actually get there, and then it'll reinforce that, and you have a gradient signal. And somehow, basically you get some back propagation coming back if you start this agent in a diverse set of locations. And for this example, you can show this is true, that you can think of this as a way to solve the vanishing gradient problem by changing the cost function where you start the agent in many different configurations. Okay, and in some systems you have access to doing this, and this helps quite a bit in practice. Okay, and we'll see there's a sense in which this is related to the condition number. And with regards to even the theory of policy optimization, we know from a number of earlier works, like this CPI-based method that Zaran referred to in the intro, is the guarantees were really dependent on the properties of having coverage in mu. Okay, but even with that, it's not obvious you'll get convergence. Okay, but right now, let's suppose we have access to some kind of mu, which gives us better coverage over the state space, and let's see if this helps us. Okay, so there's another challenge we face with policy gradient methods, which is due to optimization, right? So we're optimizing a stochastic policy that's differentiable, and a policy by nature, right, it is going to sum to 1 because it's a distribution over actions. Okay, and those of us that are familiar with optimization, optimization over constrained sets is kind of annoying because most of the time in practice, we really impose the constraint. We just parameterize the simplex and do gradient descent there. So this is what we did with these log linear policies and the neuro policies. They just sum to 1. But what's happened is, like in this log linear thing, is because we've constrained our parameter, because we've made our parameterization to always live in the simplex, the contours get squished near the boundaries. So to get a deterministic policy, you're going to get very, very flat gradients because your weights are going to have to go off to infinity, and they're all bunched up. And what this means for your optimization landscape is your gradients are going to become super flat near these boundaries. Okay, and your gradient could be super flat, even though you aren't near an optimal. Your gradient could be very, very flat because of the fact that the geometry of the way you parameterize things is that near the boundaries of this, you just have to be flat the way these continuous parameterizations work. Okay, but what we'll often do to fix this is a preconditioning idea. And with regards to distributions, the way you can do that is utilizing this Fisher information metrics. But intuitively, what you're going to do is you're going to kind of stretch out these contours to go out to infinity. So near the boundary of the simplex, you can travel faster. And that's basically what this Fisher information metric does. And what you're going to do is, rather than following the gradient, you're going to invert this matrix, which is like a preconditioner, so you move further near the boundaries. Okay? And this idea also comes up in information theory quite a lot. It's a very natural metric to use. It's also used, okay, I don't mention it here, but it's also used in some of these trust region policy optimization methods as well. Okay, so this is the optimization method we're going to look at. So rather than just doing naive policy gradient, we're going to look at this natural policy gradient. And to a large extent, practitioners use variants of this method, like this trust region policy optimization method and PPO. You can view these as variants of this method. Okay, and why do we want to analyze this? Just because we know we're going to be stuck if we just naively ran a gradient method because of this this bunching up of the contours near the boundaries. Okay, so let's look at two cases with regards to this method and what happens with convergence. So it's always good to start simple. The simplest policy we can think of is what I mentioned at the beginning, was the softmax policy class. So suppose for every state action pair, we had a parameter theta SA. What that means is you can parameterize every possible policy. So every possible policy in your world lives in this policy class. Okay, obviously, this is impossible to use in any high-dimensional problem because the states and actions could be uncountably infinite. But let's just start simple and look at this algorithm in the simplified case. Okay, so the natural gradient update rule is to just update your parameters following the gradient multiplied by this inverse. Okay, but for this form, it actually has a pretty curious form that it looks like a soft version of this algorithm I showed you right at the very start. So this algorithm we discussed at the start was policy iteration. It was this iterative scheme. We compute Q, update the policy, then are greedy. So this algorithm in the tabular case is really just a soft version because we're amplifying our probabilities based on the Q function. So if our learning rate here is infinite, in one step, we're going to jump to the greedy policy. Okay, so this is, again, it's not a convex optimization problem. So there's no reason it should necessarily converge, but this particular natural gradient update, it really has a very elegant connection to policy iteration. It's just like a soft way of doing these updates. Okay, and then again, this is for this tabular case. Okay, and but on the other hand, like, look, this is a non-convex optimization problem. So one question is, what happens if we run this update rule? Okay, so again, all I'm going to do is ask the question, suppose I exactly ran this update rule for the simplest case, which is the softmax policy parameterization, where I can represent every policy. And our question is anything good can happen? Because you can provably show this is not a convex optimization problem. Well, it turns out you will converge running this update rule. You'll actually converge very quickly and at what optimization people call is at a fast rate. So it's also a little surprising from the optimization perspective that after you do T updates of this algorithm, you're going to find a policy that's near to optimal at a rate of 1/T. Okay, so this is what optimization people really like. It's converging at a fast rate. Okay, and it's only got sort of a factor of square based on your horizon. And particularly surprising is that there's no dependence on the number of states and actions in the world. So this is the iteration complexity of this algorithm is independent of the dimensionality. Okay? And so this is pretty interesting because the problem isn't convex. We're actually getting a very fast rate, and in terms of the number of iterations, and the rate is dimension free. Okay, and when you see things like this, it's actually one should typically pay a bit of attention to it because these aren't like convex analyses, but there is some way in which the analysis is working. And I definitely recommend looking at this proof because it's somehow very short and it's making some interesting connections to mirror descent online learning, actually based on a much earlier paper where it was, the motivations are a bit different, but it had some of the technical ideas and you could extend them to get this fast rate. Okay, but this way of thinking is really provided one of the basis of how we think about policy optimization, and it really just goes back to this mirror descent style of analysis for this non-convex problem. But it works, and you get this fast rate. Okay, and you could say, look, why do I care about the tabular case? Because in practice, we run in high dimensions, we use neural networks. Well, the first question is like, look, if the gradient method doesn't even work there, it's pretty bad. But the next hope is that if you could understand that case, then maybe you could get some intuition of how you deal with, approximate gradients and large state spaces. Because right now, how are we solving this hard instance? Well, we're solving this hard instance because we're using exact gradients and we're preconditioning. So somehow we're exponentially boosting what's happening here. But the hope now is now that we've kind of established the fundamentals of the tabular case, can we move beyond this to the questions we care about, which is what happens with large state spaces, sample gradients, and approximation? Okay, but what's very nice about this is not only does this algorithm work very well for these large state spaces, like it really is one of the core tools we use in this method. The functional form of the updates are, again, very, very elegant and interpretable. And we have some ideas for how to do the analysis. So rather than fully jumping to the neural case, which I'll point you to a paper to look at, we can just look at one step of complication, which is these log linear policies. So now we look at these featureized policy classes. And these can, again, deal with large state action spaces if this feature dimensionality is small. Okay, and what we're going to look at here is we're going to assume that, so the functional form of this natural gradient algorithm is actually interesting in this case as well. So in the tabular case, the functional form was this rule, but it was equivalent to this soft policy iteration. It turns out something very similar is true for linear features as well. That suppose for a moment you did a linear regression of your features to the Q functions. Okay, and you're going to fit them. You're going to fit these under some, starting distribution mu. Hopefully that's spread out, and then you're going to run your policy. So you're going to fit this, this W to best fit these Q functions. So that's straight up linear regression. And then it turns out this preconditioned gradient method is actually equivalent to, again, a soft policy iteration update, except now we're approximating these Qs with a regression. Okay, so it's a very clean form, again, that this natural gradient, which really is a gradient update rule, when you look at what it's doing to the policy, is very much like some type of approximation to the Qs and then a soft update rule. Okay, and so what do you do in practice? Well, rather than fitting this exactly, you can just do Monte Carlo rollouts to get samples. So you're going to start at this mu, get rollouts. You're going to do a linear regression with samples. And now we run this update rule by solving this matrix inverse, which is equivalent to this here, or solving this regression. And we just draw samples. Okay, so now we don't have exact gradients. And maybe there's error in our policy fit. Okay, so now the question is like, how well do you do? Okay, and what about this measure mu? Like, is that relevant? Like, how do we solve that hard instance? Okay, so I'll give you just the theorem here for a special case, and then we'll wrap up. Okay, so right now, let's make a strong assumption, this first one, which is realizability. Because I already gave this hard instance earlier with regards to representational learning. So suppose these features could actually be perfectly approximated by these phi's. So these are very good features. This is a strong assumption, but in reinforcement learning, there's a sense in which you need it. So let's just make the strong assumption that these q's are linear in phi. Okay, so now when we run natural gradient, let's just suppose we run a regression to error epsilon, and this is cheap because with roughly dimension over n samples, that's what epsilon is going to be. This is literally just least squares regression. Again, we do this with samples from the start state distribution mu. So mu is some starting measure that's given to us. We sample from mu and fit this function with roll-offs. Okay, so this is straight up supervised learning. There's another quantity which is going to govern our convergence rate, which is going to be a relative condition number. Okay, so what properties do we want mu to have? Okay, and the properties intuitively are just like in this bad case, we kind of can't start the agent just here and get a flat gradient. We kind of want to start our agent in a way that's spread out that, that sort of tells us something about the optimal features. Okay, so what we want this mu to do is we want this mu to have coverage over the ways in which the features vary under some optimal policy. Okay, so this kappa is not really a function of the size of the state space. It's really a relative condition number based on the dimensionality of the features. And what you really want your starting distribution is to give you features that kind of spread out all over the place. Because if you want spread out, then you could have a flat gradient. But as long as this starting measure kind of gives you a nice volume for the way these features are spread out, that'll kind of cover where the features under the optimal policy. Then what you can show is, again, a dimension-free convergence rate where after t iterations, this is how good you do. So now the rate's a little slower because you're dropping like 1 over root t. But again, the iteration complexity has no dependence on the number of states. Okay, it's no dependence on the number of states. It's only logarithmic in the number of actions. And we have this mild increase in error that's based on the supervised learning error. And this could be very small because epsilon drops by just a dimension of the features over the number of samples. And it's determined by this condition number. Okay, so now we actually have some understanding of function approximation in various classes. You can generalize this to the case of neural policies. And you can look at one of the upcoming papers for this. And also, Zaran and Zaran have a nice paper using very similar ideas with the NTK approach to get a convergence rate for neural policies under various conditions. Okay, so let me just wrap up and by pointing out that, look, we've seen a lot of progress in reinforcement learning and dealing with the infinite table. And I surveyed some of these results with regards to representational issues, modeling issues, and really an exciting new direction on how we understand these policy gradient methods being theoretically sound, because they are one of the bread and butter methods in reinforcement learning. And this last slide, I made this strong realizability assumption. In an update to this paper will give a nicer interpretation of what happens when this model misspecification. And like more broadly, I think this talk was about giving a survey of results, not just mine, but also this. It's a very vibrant community, and everyone's welcome to participate. I think ML and RL, AI, they're really great communities. One should definitely participate. There's lots of exciting new questions here with regards to getting optimal rates, exploration, how we deal with like model misspecification, and this is joint work with a number of really terrific colleagues over the year. And thank you very much for having me. And I'll be happy to take questions.
Okay, let's thank Professor Kakade again for the great talk. So we have almost 1,000 audience just now across different platforms.
Oh, nice.
And so maybe, thank you very much. So maybe let's just look at the questions. So this question asks about the last part of your talk. Does kappa hide the dependence on the S and A in the definition of kappa?
No. So I don't know who asked the question. Maybe. So I don't know if you're asking about the relation to like concentrability coefficients and mismatch coefficients. But what's nice about this statement is kappa generally does not hide a dependence on S and A. So, I'm going to answer this in a bit of a technical manner, that if you understand the mismatch and the distribution mismatch and these earlier ideas of concentrability, the reason it's not appearing here is because we're making this realizability assumption. So this kappa truly is, literally you can think of this as, look at the covariance matrix of phi's under mu. Because this is literally just, the denominator is really just x times the phi transpose matrix under mu. And you compare that to the phi transpose matrix under kappa. So if you had access to your problem, like a general model or something like that, you could just randomly start at mu's that are spread out a bit, and there's no hidden dependence on the number of states and actions. Now, if there is model misspecification, so if this realizability assumption doesn't hold, then this is no longer true, okay? And that's where I'm alluding to this result I said at the very end, that wait for the forthcoming paper, that once you kind of relax this, this model misspecification assumption, then all of a sudden it's a little more subtle how to think about this, but it's still going to be a stronger result than the previous ways in which we hid the state action dependence. So I hope that answered your question. I wasn't totally sure if you were coming at it with more background, but the short answer is no, it doesn't hide it.
Okay. So another question is regarding how to implement the natural policy gradient in practice when it comes to when you also incorporate functional approximation in it.
Yes. So okay. So you're asking how to implement it when you incorporate function approximation.
Yes.
Okay. So in a sense, this the algorithm, if we go back to here. Where to go? Sorry, if we go back to here, it is not at all hard to implement with function approximation, because you're just inverting a matrix. Like this works for neural networks. Like and not just these linear policy classes. Like you're literally just, so look at this term. This term is just your vanilla gradient of a neural network. And there's Monte Carlo ways to get your gradient with respect to your parameters. Okay, and this is the inverse of your Fisher matrix. So neural network people like Roger Gross, like these parfact things, that's basically what they're doing in neural networks. They're trying to use parfact to implement a Fisher inverse times your gradient. And there's like conjugate gradient methods to do that as well. So what I'm showing you is a regression interpretation of it, which is helpful for theory. But the way to implement it is really just, can you do matrix inverses? But in practice, things like conjugate gradient works. And I don't know if the OpenAI one for the most recent one did TRPO, but I'm pretty sure they did. Like the earlier hand demonstration ones was actually parallelizing this matrix inverse in a batch kind of mode. So there really isn't a problem with implementing this with function approximation. And look, you even see that here, because in this case of linear policies, the algorithm itself doesn't, you don't need these things to have zero error when you apply it. You just solve this regression problem and update it. And this is the algorithm, whether or not you had whether or not you have error or not. So it's a pretty straightforward algorithm. And it really is the same thing as TRPO as well. So there's like basically packages that do this.
Mm-hmm. Thank you. So another question is regards of the representation learning. And so in TRPO or in natural policy gradient, suppose we parameterize the policy and value function using different sets of features, and then when in this setting of we have feature mismatch, is it possible to say something about the from a theoretical perspective?
Right. Okay. So let me see if I understood the question. So you're asking about possibly using features which have mismatch, and I believe your mismatch means they might not satisfy this realizability assumption. Is that? Sorry.
Yeah.
Is that the question?
Yes, and maybe they are not compatible.
Yes. So okay. So what do you mean by compatible?
Oh, that is we are parameterizing. We are estimating Q theta using a different feature instead of phi, but phi is a feature used by the policy.
Oh, I see. But note the algorithm itself when you run it in practice. Okay, right. So that's fair. So sometimes what people will do is they'll estimate Q with some other method and plug it in, but you could just pretend like that's part of your policy fit anyway. So what's nice about the analysis here is it doesn't really matter if it's these features or not. It's really just a property of the fit of your Q function when you do the soft update. Okay, so think of, morally just think of using this update rule. Okay, and that is what the natural gradient and TRPO are doing. And what matters is the quality of your fit for that update. Okay, and the quality of your fit, now that's a far more subtle issue because in practice, we typically don't have this realizability assumption. Okay, and now maybe I'll just give you a bit of a precursor to what we're going to reformulate this as, is that if there's error in your fit, like for example, suppose if you had infinite data, your features, however you come up with them, they aren't going to perfectly represent the true Q, which is always the case in practice. Like your network is never going to perfectly approximate the Q. Then the question is, how does the errors get amplified? And what I'm going to argue is it's really a very close connection to transfer learning is the way to think about this. But I think just wait maybe 2 weeks and we'll update the paper to do this. The paper right now does have some connections for this. But I would say, like, look, this is the 20-year-old question in reinforcement learning, that when there's error in any of these methods, often they get amplified very, very badly. And this realizability assumption shows that that doesn't happen, but we're really interested in what happens when there's model misspecification. So it's a very good question.
Okay, thank you. So another question is, could you please elaborate more on the open problem related to the policy gradient and agnostic setting?
Yeah, okay, so so I think this is more stylistic, that so let me just bump up a level, and what do we mean by agnostic learning and supervised learning? So in supervised learning, we often talk about doing best in our parametric class, right? Like, forget about computation for a moment, but we typically don't assume our features are good in any sense, but we just want to find the best linear fit against this distribution. Okay, and we can do that with some number of samples. Okay, and largely, once you move away from some of the statistics, once you move more toward maybe like uniform convergence and empirical process theory, our ways we think about agnostic learning and supervised learning don't make underlying assumptions about the world. Okay, but in reinforcement learning, we really do have to make much stronger assumptions about the world, and we see that even in this this representational learning result over here, which I guess is okay. Now it's back on the screen. That here we're making a very strong assumption of what our policy class satisfies. Okay, and at the very end of our talk as well, here we also made a very strong assumptions about our policy class. And what I mean by agnostic learning, it isn't a hard, it isn't like a precisely phrased open problem, but it's an open problem where we'd like to have stronger statements about how well we do in reinforcement learning that deal with some kind of model misspecification or non-realizability. And there's definitely a lot of progress. So I know like Zaran and Zaran have some very nice work on linear MDPs as well, that there are classes of models where you really can generalize, but these classes aren't really about function approximation. They're assumptions about the way the world behaves. And I think this is just a broader effort of how can we get stronger guarantees when our modeling assumptions might fail. And so I think, so I think it's more, it's partly conceptual, but there is a sense when some of these old policy gradient methods are more robust in this sense. So I think, once we update our policy gradient paper, some of these will become a little more clear, but part of this is a bit stylistic too, of just what are the ways in which we can make progress with reasonable relaxations of these hard modeling assumptions that we typically make.
Okay. Thank you. Maybe the last question. So, is it possible to comment on what should we do when the state of the system are not directly observable?
Right. So the question is, what do we do when the state of the system isn't observable? And the framework for dealing with this is often referred to as POMDPs. So this is the partially observable Markov decision processes. Now, the kind of usual answer, which is a cheat, is that if you do policy gradient methods, there's a sense in which the algorithm itself, it doesn't really matter if the state is observable or not, because as long as you parameterize the policy, like you could parameterize the policy with respect to the history, and you could take your gradient. Of course, that doesn't necessarily mean you're going to find something good. So I think the question of how do we actually do reinforcement learning when the state is observable, I think this is a very interesting question. And in particular, how do we couple it to capture long-term dependencies of the past? And we know these problems, like in the worst case, could be very, very challenging because there are like exponential lower bounds on the horizon. And we know that like learning HMMs, like some of the, there's various spectral and tensor-based methods, which does give us provable learning. But when HMMs might have certain types of dependencies, there's also like cryptographically hard instances. So I think the short answer is there's a lot of really interesting questions of once we move to partial observability. But part of this is how do we get practical algorithms in doing this? And maybe I'll end with just a broader push of how I view theory in this space of reinforcement learning, that and contrast this to supervised learning. So in supervised learning, I would say our theory is largely explanatory, that we're trying to explain why deep learning works. And I think this is important because it's fundamental research, like why are we not getting stuck in these local minima in supervised learning? But in reinforcement learning, and this is partly related to your partial observability question, this quote-unquote theory, it isn't really just theory. We actually want better algorithms here. And how we get better algorithms that say explore and are robust, they're both like mathematical foundations can genuinely help. So this isn't explanatory. It's like, I think I would say RL in the algorithm design, it really is a pretty rich interplay between theory and practice. And this is also going to come up in partially observable Markov decision processes, that we actually want better algorithms here, because it isn't this situation where practitioners have good algorithms already. Like in supervised learning, just run SGD, it works super well. In reinforcement learning, the space is we actually want better algorithms, and we're not trying to just kind of explain what practitioners do. Practitioners are actually looking at both theory and empirical insights and and the study of algorithms to actually get better techniques. So, on that note, I would say, partial observability is a pretty interesting question there, and our motivation is, again, really getting new, both practical algorithms and principled algorithms. And I think this is a really interesting space we can do that in here.
Okay, thank you. I'm running out of questions. Thank you, Professor Kakade, again.
Yeah.
So let's finish here maybe. And also thanks everyone for joining. We are looking forward to seeing you guys next week.
Yeah.
Thank you.
Thank you.